First, let me remind you that one of the main goals in this course is to be able to describe the spontaneity of chemical processes under conditions that differ from the standard conditions. That is, under conditions where the substances involved in the process are not pure but are mixed with each other. So far, we have studied spontaneity in processes associated with changes in pressure, volume, or temperature for a pure substance in a single phase. We have also dealt with the case of systems containing a pure substance in multiple phases. Now, we are going to discuss the case of mixtures of multiple components. We will deal principally with gas and liquid mixtures and not say too much about solid mixtures. While the latter are more important in the field of material science and engineering, they will not be treated here. However, what we are going to learn, especially on the topic of liquid mixtures, can be readily applied to solid mixtures. In Chapter 3, we will not deal with salt solutions. These will be discussed in Chapter 5. In Chapter 4, we will use much of the material learned here to discuss the spontaneity of chemical reactions, accounting for the mixing of reactants and products. We will start this lecture with a brief and necessary review of the terminology that is used in the context of solutions and mixtures. This review will include a non-exhaustive descriptions of the various approaches used to describe the composition of mixtures or the concentration of specific components in these mixtures. We will then introduce the concept of partial molar properties for the different components of a solution and contrast these with the molar properties of a pure substance. This will include definitions of the partial molar volume, partial molar energy, and partial molar entropy. With these new properties in hand, we can define and discuss the partial molar Gibbs energy of a substance in a mixture, which we will very appropriately refer as the chemical potential. We will then learn about the implications of equilibrium in a mixture on the chemical potential of its components. We derive the very useful expressions for the chemical potential of ideal gases and use this expression to discuss the chemical potentials of solvent and solute in a liquid mixture. We then consider the specific case of ideal solutions and review Raoult's law. We conclude this lecture with a derivation of the Gibbs energy change associated with isothermal mixing to form a homogeneous binary ideal solution, and use the expression of delta G of mixing to learn more about the characteristics of ideal solutions.